Yes, I will continue where I left off yesterday. So let's recall briefly where we ended yesterday. We were just busy discussing the Hamiltonian picture for conformal field theories. We, in particular, decided to look at conformal field theories on the cylinder like this, and we were going to investigate a Hilbert space of states defined on this spatial manifold, on this configuration. And then by a conformal transformation, or more precisely a diffeomorphism and a Bell transformation, I mapped this cylinder to basically the plane, and the Hilbert space of states defined on the cylinder like so becomes the Hilbert space of states on a ball on a sphere in the plane. And time evolution on the cylinder becomes dilatation on the plane or in Euclidean space, and therefore this is also called radial quantization. We had then the idea that we should do the following things. We should investigate the action of the charges. We did that, and this in particular led us to the algebra of charges, which was SOD plus 1, 1, the conformal algebra in Euclidean signature in d dimensions. Then I said we should investigate the basis, and then we should investigate we should discuss aspects of complex conjugation, unitarity, and conditions that you get from unitarity in particular. We got pretty far with the discussion of the basis. In fact, I mentioned it at the very end, that the basis is really like states of this form a complete basis of this Hilbert space. So this is by virtue of the state operator correspondence. The idea that to any state that is an eigenstate of the dilatation operator, you can associate a local operator, and therefore if you just have the list of local operators in your theory, then from that you can generate this basis of your Hilbert space. And these operators organize nicely, or these states, they organize nicely themselves in representations of the conformal algebra. So for this one, I've made it a little bit more explicit. So you start with something that we call the primary state, primary operator, which has the particular property that if you act on it with k mu, you just get 0. So this guy is killed by k mu. It may transform in some representation of the SOD Lorentz or rotation algebra. So then it give it an extra index A. And the rotations, they of course act. They just change this index A, and they don't do anything else. And this has a dilatation eigenvalue delta, where delta is some real number. And then, of course, you can act on this with p mu to generate derivatives of the operator. These are called the descendants. They're not primary, and k mu moves you up in this tower. So for every primary operator, we have this gigantic tower of operators, and that's one set of vectors, and that's going to be part of the basis. Now you repeat this exercise for every primary operator in your theory. For example, the stress tensor turns out to be a primary. You generate your tower. That's also part of your basis. You have a new operator, say x. Well, you generate the tower, and that will also be part of the basis. Yes? Yes, very good. In 2 dimensions, what happens? In 2 dimensions, the algebra is not SO, the conformal algebra, which we got from, in principle, from solving the killing vector the conformal killing vector equation. Right? Something like this, maybe 2. So you find all the vector fields that obey this constraint. And then I said in general dimensions, not equal to 2. This is the set of, you find a finite set, and this finite set generates, from that you build the charges, and from that you get the algebra, and the algebra obeys this. Or you just take the algebra of vector fields, that would do also. And then from that we discuss the representation theory. So in 2 dimensions, at this step, you get extra stuff. Because in 2 dimensions, it turns out there are infinitely many solutions to this equation. This algebra becomes gigantic. It becomes the DeWitt algebra for the vector fields and the Virasoro algebra for the quantum theory. Then, of course, the representation theory, there are many more charges now. So this representation and this representation may be related by a Virasoro transformation, the action of a Virasoro charge. And so all of these fall into much bigger representation of the full Virasoro algebra. So everything I said here is true. They definitely, if I just ignore the Virasoro algebra completely, and I just look at the SO3,1 subalgebra, then everything falls nicely into these representations. And with that definition, the stress tensor is a primary. But if you now give me extra charges to work with, I can have more relations between the states. And in particular, then you see that the Virasoro is actually, the stress tensor is a Virasoro descendant of the identity operator. But that would involve an extra charge that just acts between these or extra charges that acts between these representations. I will just completely ignore Virasoro symmetry. In fact, we'll do a little bit of numerics, hopefully in the final lecture, but in d equals 2. And then I'll just pretend not to know Virasoro. And that's fine, right? It's consistent to just closurize towards extra symmetries that you have. You may not get the most powerful constraints, but it's definitely, you don't get a wrong answer. So thanks for that question. I wanted to stress that anyway.
Why the stress tensor acting on
The stress tensor on? The stress tensor inserted at 0 does not give 0.
Yeah. Why did this thing did not give out a 0?
The stress tensor is a non-trivial operator. We never said the trace of the stress tensor is 0 in some sense. It's contact term singularities, but that's it. But the stress tensor itself is not 0. It's just some operator. What was 0 was the divergence of the stress tensor, for example.
But it's acting on the vacuum, and the stress tensor of the vacuum is not 0?
No, the divergence of the stress tensor is.
Oh, okay. Thank you.
So let's resolve that confusion. I said if you act with the dilatation operator or something on the vacuum, you get 0. So this is the integral of, right, in radial quantization, you have this picture where you say the integral n mu, x mu, t mu nu, x. This is also a good question and something that I actually wanted to get to. So let's do it now. N mu, x mu nu, 0, where sigma is the set of is this surface defined by x equals 1. Good? This is the integral over the ball, the interior of sigma, of n mu. Well, n mu gets by Stokes' theorem, x mu. Mu, there's a mu. Right? So box mu x nu, well, that gives me delta mu nu, and that's a trace of the stress tensor that I'm not considering here anyway. So I should say this to be a traceless tensor. And then there's another thing, which is that box mu t mu nu equals 0. Away from other, up to delta functions, but there is no, up to contact term singularities, but there's no other operator. So the derivative, the divergence of the stress tensor is 0. So as it happens, your question is excellent, because so what happens here is that this operator is a perfectly fine operator, but now if I act with p mu on it, I get something that's 0. So here, I act with p rho, or I get something like d rho t mu nu, 0, 0, at the first level. And here there is a state, if I contract these two indices, I get 0. And then there's sort of the traceless bit, which is not 0. So this splits into, representation theory-wise, this splits into this and d rho t mu nu 0 well, up to symmetrization, and so minus delta rho mu, dot, 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 right? And this guy is not there. It's equal to 0. And so this whole tower has now sort of a 0 state. And if I act with p mu's on it, I get another 0. Of course, I still get 0 and 0. So this is actually something I wanted to say, that this tower, at a slightly later stage actually, this tower, sometimes there's some states in this tower that are 0. And those you just throw out. In most cases, there are no such 0 states, but sometimes there are. And those you have to throw out, like here the divergence, and anything you get from this divergence of the stress center acting with further p mu's. So those you just cross out. In fact, I wanted to get to something, so one other operator, which is the identity operator acting on the vacuum, is the vacuum. So I wanted to mention that the identity operator for various reasons, two of which is that there is a state operator correspondence. So you could ask, well, if you have a state, there should be an operator. If I give you the vacuum, what is the operator? Well, it has some super trivial, it has to be some super trivial operator. And in fact, it's the identity operator. So technically, to complete this notion of a state operator correspondence, I need to add in my list of local operators the identity operator, which is just, it does nothing. It's really boring. But the identity operator is another example of an operator where there is not such a tower of descendants associated to the identity operator. So the identity operator is the property that if I act with p mu, I just get 0 immediately. I don't get a new state. So the identity operator, for the stress tensor, we saw that the particular state in the tower became 0, and we have to throw it away. For the identity operator, there's no tower, and there's no descendant states. So these representations are called short representations. They're special representations of the conformal algebra. And they just happen to have certain states that you have to throw away because they're 0. So we'll get to, of course, now you would have to analyze why, for certain values of delta and spins, and so there may be these kind of vanishing states. And we'll get to the analysis of when these states vanish and so on when we discuss the consequences of unitarity here. So the details for now, let's just say that sometimes there are states, there are descendants that vanish. And I've given you two examples, the stress tensor and the identity operator. But I haven't told you when this happens in full generality. We'll get there at some point, hopefully today. So, any more questions? Yes? We'll just do Q&A today.
Oh, so since I'm more familiar with 2D, in 2D, when you go from the plane to the cylinder, you have this shift in the vacuum where you
Yes.
have this 12 over C, C over 12. So what is the analog of that for higher dimensions?
Well, all of that is related to the conformal anomaly, which, right? So what does this map involve? It's a diffeomorphism and a Welby scaling. And if you do a Welby scaling, your partition function changes with an anomaly, could have an anomalous term. And I was going to ignore that anomalous term, and I kind of want to keep ignoring it. But that's a thing that sits there, and it could mess up these things. And in 2 dimensions, you see that your vacuum energy does a shift. But also, for example, that the trace of the stress tensor is not exactly 0 in curved space. It's C over 12 times the scalar curvature. And you get exactly similar things if you have an anomaly in higher dimensional theories. But as long as you work on flat space, you don't get to see these issues. So it's fine. Okay, more questions?
So I'm a bit confused. So identity operator is a primary.
Yes.
If you act PMU on identity operators, you get 0.
Yes.
And then its eigenvalue for the rotational operator is 0, right?
Yes.
But here you say by acting PMU, then you get one more higher dilatation eigenvalue, right?
Yes. Well, if you don't get 0, right? So
yeah.
for example, by acting with K-mu, I get one lower dilatation operator,
Yeah.
or I get 0.
Yeah, yeah.
And then it's just 0, and 0 is not a state.
I see. Okay.
A good state. Yes.
So can you repeat the reason why there must be some primary operator, which means there must be a state that K-mu operate on it will get a 0. Right? Can you repeat the detail?
Yeah, there are 2 reasons I can give. One will come here. This will show that delta is greater than or equal to 0. But we haven't discussed this yet, so I cannot explain that reason at this moment.
Okay.
But it'll come. And the other is that generally, if you take the 2-point function of an operator, like this, any operator, just by scaling variance, it goes like 1 over x minus y to the 2 delta. Now, if delta, right, if k goes on forever, there are operators with arbitrarily negative delta.
Yeah.
If there are operators with arbitrarily negative delta, this correlation function increases at larger and larger distances.
Yeah.
That's not something I'd like to happen in a normal conformal field theory. It might happen in a non-unitary theory or whatever, but it's not what we usually call part of the usual framework of conformal field theory or quantum field theory even. We want this thing called cluster decomposition, where if you do an experiment on Mars and here, these things should not meaningfully influence each other. So,
Yeah, so just violate the unitarity, right? So
here it's sort of a consequence of locality, really.
Yeah.
Yeah, we can also show it using unitarity. Yes, more questions. Okay, good.
For 2D metric, and every metric is conformal equivalent to the flat metric. So does this mean that the radial quantization is somewhat a little trivial in 2D case?
I'm not sure why it would be trivial. Every metric you say is conformally flat, but I'm not sure what the bearing is on radial quantization. So what is a quantization? In my perspective, it's just some foliation of space with some slices that you're going to call constant time slices, and then you evolve from one slice to the other with something you call a Hamiltonian. And in flat space, I could have picked a slice like constant time slice, evolve like this, or evolve outward, or whatever. And that's quantization. So whether metrics are conformally flat or not, has nothing to do with that. And I've just chosen radial quantization because it's super convenient. The reason I chose radial quantization is because of this, because the states in radial quantization are in one-to-one correspondence with local operators. So that's beautiful, and I wouldn't have that if I had chosen a different foliation. Now the statements I just made don't depend on metrics being conformally flat or not, whether I'm in 2 dimensions or not. This is just a statement about the choice of quantization.
Yes, but for 2D case, does it mean that we can easily get the correlation functions for any metric, just from this simple transformation?
That is correct. But yeah, okay, sure. But we're not going to be interested much in being in the correlation functions in any background metric. I'll just be interested in the correlation functions in flat space, mostly, of local operators in flat space. And so the fact that you can then do a Bell transformation to reach an arbitrary metric, fine. Okay, it buys you more, but it's not something I'll be discussing much. Having said that, of course, even in 2D, I mean, you can do a Bell transformation, but you cannot change the topology, right? So in 2D, if you give me the correlation functions in flat space there's not. You have to do quite a bit of work to get to the correlation functions on the torus or a homogeneous Riemann surface, right? It's not just the Bell rescaling, because Bell rescaling cannot change the topology. Okay, good. Lots of questions. I'm happy that I already got to introduce these so-called null states, these states that vanish in this tower. Because that'll be important later on. So for the state operator correspondence, let's do something. So let's use this state operator correspondence to derive the following. So let me prepare a state with two operators, O1, O2, I chose it to be at 0, and O1 at x. Now I do this path integral and I stop at this point. So this, at the boundary of this ball, so this will prepare some state in my theory. So the state we now have come to denote it in radial quantization as like so. O1 of x, O2 of 0, acting on the vacuum. This is a state, and because of the state operator correspondence, well, it's a state in Hilbert space, so I should be able to decompose it into whatever basis I have, and because of the state operator correspondence, the basis should be stuff of this form, including perhaps the identity operator. So there should be, just by the state operator correspondence, and the whole discussion of the state operator correspondence is basically to allow me to write this equal sign. So this is by state operator correspondence. There should be some decomposition with some coefficients that depend on the operators in question, that also depend on x, where I inserted the operator, in terms of the basis vectors on my Hilbert space, which are of this form, for some local operators, okay. This must be true, and this must be a convergent sequence, otherwise this is not a good basis. So this is nice. We can make things even a little bit nicer by realizing, well, these operators, they come in two forms. They come in the form of either primaries or descendants. So we can say, let sum over primaries only C1 to K X. And then absorb all the descendants in some redefinition of these coefficients C1 to K. So these are different CKs, so let me add a tilde to the first one. I don't want to carry the tilde around. And then I have a primary operator. Right? I haven't done anything. I've just grouped all the operators into the right, into the representation of the conformal algebra. And I've adjusted the sum accordingly. And this d mu, of course, acting with d mu takes care of, well, gives you a descendant. So in general, you may need infinitely many descendants. And so in general, this would be a differential operator of infinite order. So it's an infinite order non-local differential operator. So this is true by virtue of the state operator correspondence. And that's already quite nice. But now we'd like to see if we can say something about this complicated beast C, this object C, which depends on x and the operators in question, C1, 2. So like I said, it depends on the three operators, 1, 2, and k, of course, is just some coefficient in some basis decomposition of this state. Now let's deduce something about the C's. Let's do the following. Let's consider the state O1 of x1, O2 of 0. So we have our state again. Well, I already drew the picture like this. And we're just going to take the expectation value of O3. We added at some point x3. So maybe in radial quantization, you would have an out vacuum and an in vacuum. And this generates the state, and then we measure O3, the overlap between this states given by O3, technically O3 dagger, acting on the vacuum. So we can compute this correlation function. Here's our state. So this I should be able to decompose into the basis, and then I measure with the third operator, O3. So let's substitute this thing. This should be true. So this should equal O3, x3, sum over primaries, C1, 2, k, x, d mu. Do I do this right? So x, I need some, okay, x1 d mu, oh, hence k, 0, 0. So this must be true. Otherwise, my state operator correspondence would not work. But now I have this complicated differential operator, but it acts on something very simple, namely a two-point function of primary operators. And let me suppose that O3 is a scalar. Let me suppose that everything is a scalar, so there are no Lorentz indices hidden anywhere. Then I see that this is sum over k, C1, 2k, x1, 2, dd x2 mu acting on, well, the two-point function of scalars in a suitable normalization is just delta k hat 3, 1 over x 3 minus x2 to the 2 delta 3 at x2 equals 0. Right? This is what I get. I have a two-point function. This is the two-point function. There's a delta, there's a coefficient there, which I think I said is I'm going to normalize to delta ij, and I have x3 minus x2 at x2 equals 0. So I introduced an x2 here that I set to 0 so that I know what my differential operator acts on. And then I should call this x1 minus x2. Okay, everybody still on board? Of course, now this delta k hat 3 kills the sum. Sum over primaries k hat. The sum goes away, and the delta function just becomes 1. So what we get here is this complicated differential operator that I want to know something about, acting on the two-point function. And I get the constraint that this better equal the three-point function, because that's what I've just derived. But the three-point function I know, because the three-point function was completely fixed up to a single number by conformal invariance. It's lambda 1, 2, 3. And then you have x1 minus x2 to the delta 1 plus delta 2 minus delta 3, and two other terms. So what I get is that this C1 to k, which in principle could depend on the operators involved, and in some very complicated way, these are just three operators in the theory, is actually almost entirely, up to this thing, is fixed by conformal invariance. More precisely, I see now that the C1, 2, 3s so I get an equation of the form that C1, 2, 3 is basically lambda 1, 2, 3 dot, dot, dot. Lambda 1, 2, 3, that factor just comes out in front. times some new guy, C tilde, which only depends on, well, let's say this in a second, where C tilde of x12 ddx mu2 acting on the 2-point function x23 to the 2 delta 3 equals 1 over x12 to the delta 1 plus delta 2 minus delta 3, and then the two other guys that I'm not going to write. Right, so this is what C tilde must do in order to reproduce this thing. So the information that is theory dependent, the lambda 1, 2, 3, factors out of the C, and C tilde is just some complicated differential operator that when it acts on the 2-point function should reproduce the 3-point function. So if you look at it, this is an equation for C tilde, and so we see that it only depends on the deltas involved. More generally, if the operators had spin, it would also depend on the spin of the operators. But it doesn't depend on anything besides the representation, quantum numbers, delta, and spin of the 3 representations involved. And so, in this sense, the C tildes are completely fixed by conformal invariance. If you give me the quantum numbers of 3 representations, in other words, you give me the deltas and the spins for 3 different representations, then I can write down the corresponding C tildes. I don't need, this is not theory dependent. It's just a function of the deltas and the x's. No matter which CFT you're looking at, you always get the same C tildes. And the only thing that is theory dependent is the actual deltas that will actually appear in your theory, and of course this lambda, which is the 3-point. So that is quite neat. And so in any conformal theory, there's this universal structure that you can express a product, the state generated by a product of 2 operators in terms of the basis with coefficients that are almost entirely calculable. In fact, you can compute it. You can show that if you take x2 to 0, you can show that C tilde is, well, it's an infinite order differential operator, so I'm not going to write down the full thing. But for 3 scalars, it looks like this, with some coefficients that I'm also not can be bothered to compute. d mu plus x12 squared box plus dot dot dot. So this is what it looks like, just to give you an idea. And these numbers that I pair, so this pound sign means just some number that I didn't compute. It just depends on the deltas. So this idea that I can replace a product of operators in radial quantization with the sum of other operators is a thing called the OPE, or operator product expansion. And I hope these words are now entirely clear. You have a product of operators and you expand it as a sum of other operators.
So,
Yes?
Are those C's uniquely fixed, or?
I mean, if they're multiple tensor structures, they're multiple C's. They're multiple 3-point functions. But yeah, they're fixed. The C tildes are fixed. And what you need is, what you cannot know, what is theory dependent are the lambdas and the deltas. The C's are C tildes are fixed. Yeah, there's no, this equation fixes them. If you, okay, I'm going a little fast. Let's focus on scalars. I claim this equation fixes it. How do you check it? Well, you can go to take x2 close to x1, and then you can find, for example, compute these first few coefficients, and then you'll find that this is uniquely fixed. There's just no freedom. You write down the most general differential operator at a certain order. At second order, there are 2. At first order, there's 1, consistent with scaling variance. And you can compute these coefficients. So yes, it's completely fixed in that sense. Now, if these operators were tensors, there would be multiple 3-point functions. That just means there are just as many C tildes as there are 3-point function structures. But that just gives everything an extra index, a bunch of extra indices. It's not particularly important for what I want to say. I'm sorry?
It's essentially some form of a Taylor expansion about O tilde k O acting on O0. It's almost has the same structure as a Taylor expansion of a function.
An expansion?
Taylor expansion.
A Taylor expansion. No. These operators 1 and 2 are not operator.
Yeah, I mean, it's like an expansion about O tilde k O acting on.
Oh, here you want it to be a
Yeah.
Taylor expansion. I mean, it's not just a standard Taylor expansion of O of x, right? This thing does not become O hat of x. It's a much more complicated thing. It's a very non-local thing. It becomes, I don't know, you can write it as an integral equation if you want, but it's not some kind of standard Taylor series. Yes.
I'm just a little confused about where does the S23 goes in the expression of C tutor?
The last?
S23. No. The right, to the right, S23 and yes.
This one?
No. This one, yeah. Where does this S23?
Yeah, it came from here. X2 minus X3. Oh, and this is X23 is X2 minus X3.
But in the final expression of the C tutor, and there is no S23.
That is correct. Because C tilde does not, it is the thing in the expansion of this. And O2, I put it at X2. That changes. Right, I expand this thing. I just apply what I wrote there. There's no X3 inside. And so I get this, or alternatively this, if I get here, X2 was at 0. Now I move it a little bit away from 0, but it's still, I mean, I could have written X2 from the beginning. And then I have C acting on the 2-point function, and that's where X3 comes in. Should give me the 3-point function here. Right? I think my equations are correct. ddx2, this is evaluated at x2 equals 0. So here there's 0, x1, x3. And here I made x2 non-zero, but that's just a translation of everything. So that doesn't really matter. So this equation, C does not depend on x3, but this equation should hold for all x3. So maybe I should write the other terms. x13 delta 1 plus delta 3 minus delta 2, and x23 delta 2 plus delta 3 minus delta 1. Right? It's an equation that should hold for all x3. Because the C tildes, they are defined over there, and there was no x3 over there. And now I've derived it I've derived some constraint for the C tildes using an operator insertion at x3. But the constraint should be true no matter where I put the third operator. So that's why I get an infinity of constraints, if you want. For every value of x3, I get something that looks a little different. Yes?
When you decompose the states on a basis, do you need the unitarity? The unitary condition?
For the operator product expansion?
Yes. So.
Yeah, if you drop unitarity, everything falls apart.
I want to know.
I mean, why is the state operator correspondence true in a unitary theory? I used at some point that the dilatation operator was diagonalizable, and that its eigenvalues were real, and its eigenstates were a complete set.
Non-unitary conformal field theory, and the state operator correspondence is also true.
Perhaps. I have not derived it. Non-unitary theories are well. It might be true.
So for that theory, do we have a basis?
For a non-unitary theory?
Yes, because the emission operator, the eigenfunction of the emission operator is a complete basis. But for the non-unitary case, I wonder if the same thing happened.
I think I am hesitant to say anything rigorous about non-unitary theories because it's so weld. What if the dilatation operator has some complicated Jordan form? What if the dilatation operator there's no sort of organization in primaries and descendants? What if the eigenvalues of the dilatation operator are complex? What if the eigenvalues of the dilatation what if there's a dilatation eigenvalue, if it's at all diagonalizable, which is -3 + 5i, right? And everything sort of falls apart at some point. And there's very little structure that remains. If you just say a theory is not unitary, it can be super weld.
So we will lose OPE.
I think so. I mean, you may find a class of non-unitary theories, or classes of non-unitary theories for which the OPE still holds.
Okay.
That's not, but I don't know how to prove that the OPE would hold in general if your theory is not unitary.
Okay, thank you.
Because I cannot get to this state operator correspondence even. Right? State operator correspondence implies OPE. I think that's rigorous. But the state operator correspondence is the hard part to show. No questions? Okay, now, yes?
Chosen or not?
Yes, x3 is arbitrary.
So for the left hand side, I choose x3 to be x1, and it seems the equation, the left hand side of the equation is finite, but the right hand side of the equation.
You're too precise. Yes, x3 is arbitrary, but not x1 or 0 or x2. Of course, you get what will happen is that you get some Here I wrote C tilde as an infinite sum of differential operators. And what will happen is that this sum will not converge. It'll just be when it acts on this thing, when x3 is equal to x1.
So what's the restriction of the x3?
Actually, there's a fun story. Yeah, you can ask, well, this will certainly work. So if x3 is outside the disk around 0 that contains x1 here, then it's fine. Otherwise, you have to be a bit more careful. You can if x3 sits between O1 and O2, then this thing will not converge, for example, because then you're in trouble. Because then this does not, right? I need to have this picture that I have a state and then something else. But if operator 3 is going to mess with my state, then things that get more messy. So yes, thanks for that question. Of course, you can do a conformal transformation and map this sphere to another sphere, and then you may be safe. But
thank you.
So yeah, okay, no, never mind. Let's leave it at that. Now let's jump ahead a little bit, because I can see that I'm running out of time and I want to get to the Bootstrap also, because that was part of my assignment, and that's where the fun starts with all of this. So let's skip for a moment this discussion of unitarity, and let's just get to the conformal block decomposition. So for this, I will look at, none of the black things are still working. For this, let's look at a 4-point function of scalar operators. And let me organize the 4 operators in such a way that I can apply the operator product expansion. So in particular, I'll put 1 here, I'll put 2 here, and then 3 and 4 are somewhere outside. So I'm in a good position to apply the operator product expansion. What you will get is that, well, you can apply the operator product expansion to fuse 1 and 2 together into a sum of operators. But you can also apply operator product expansion to fuse x3 and x4 together as a sum of operators. So what you get is that you have lambda 1, 2, k hat, lambda a sum over k hat and l hat. Then we have this complicated differential operators, which depends on the delta. So there's one that depends on delta 1, delta 2, delta k. In fact, the operator that appears can also have spin, so it also depends on lk. But let me assume that these 2 are scalars. And then it's something that depends on x12 and L2. That thing, then for 3, 4, I get the same structure, delta 3, delta 4, delta L, spin of L, x3, 4, delta 4. And then, of course, I have operator K, operator L, primaries. One sits at x2, the other sits at x4. Like so. Like I said, these operators can have spin. As it happens, if you have 2 scalars, only tensors can appear, symmetric traceless tensors. So these have some index A, and these have some index B. And this should really have an index A also, and an index B also. And A here is short for a symmetric tensor, mu1 to mu L. So this L here is just the number of mu indices. And this should be completely symmetric and traceless, because if you have a trace, then that's a different representation. So these are the only tensors, as it happens, that can appear in the operator product expansion of 2 scalars. In the operator product of 2 scalars, you cannot have antisymmetric tensors, you cannot have spinors or anything. That just follows from the fact that the 3-point function, the associated 3-point function is 0. And then if the 3-point function is 0, then you see that the OP has to be, the operator can also not appear in the OP. So this is what you get. 2 complicated differential operators acting on a 2-point function. The fun fact is, of course, that I just tried to convince you that the C's are fixed by conformal invariance, and the 2-point functions we've shown before are fixed by conformal invariance completely. If you normalize the operators to 1, then there's really no freedom here. This is just a 1. And so this whole thing, from here all the way to there, is fixed by conformal invariance. It's a complicated function, but it's a function that's just of the variables that I indicated. It's not theory dependent. If you give me deltas, L's, x1, x2, x3, x4, then this spits out a number. So we can capture this whole big thing and give it a new name. So from here to here, that thing, we'll call it a function typically denoted by curly G, which depends on all the deltas, delta 1 to delta 4, delta operator k, spin of k, and the x1 to x4. Actually, there's one more simplification as before, that the sum, the double sum that we had, because this is proportional to delta KL, the Kronecker delta, the 2-point function, I can diagonalize them, so that the only non-zero 2-point function is when operator k is equal to operator L. So this, in particular, is proportional to delta KL. And that delta KL kills my double sum. So k is equal to L. So I can just as well erase this sum, and everywhere I see an L, I just make it a k. This is a legitimate thing to do, because any other 2-point function will vanish. So if you didn't keep attention, look at me for the last 5 seconds. What I've just did is I just replaced in this equation all the L's with a k. And so now it only depends, like I wrote here, on delta k and Lk and nothing else. And it's a calculable thing. I mean, the 2-point function is fixed by the ordered entities. The C tildes are fixed by the ordered entities. And it's just known. So it's a known, in principle, known function. You can write Mathematica code that does this, that does the job for you and computes these so-called these functions. So these functions are called conformal blocks. And what we have just shown is that there is a so-called conformal block there's not a, the sum doesn't go away. The double sum becomes a single sum, but there's still a sum of primaries. So what we've just shown is that there's a decomposition of this 4-point function into a sum over primary operators, where each term in the sum is, has this product of 3-point function coefficients and then a known function, which is called a conformal block. So this is the conformal block decomposition of a 4-point function of a 4-point function of scalar operators in this case, in a conformal field theory. And if I put my operators in the indicated configuration, where 3 and 4 sits outside the ball generated by 1 and 2, like so, then this is a completely convergent expansion. So, in short, O1 to O4 depends lambda 1 to k, lambda 3 4 k, g delta k, lk. This is more typical notation, delta I xi. Sort of. And this is, again, the same. It's the same thing, the conformal block. I just wrote it in a notation that we more typically use in the CFD literature. But I'm not done yet, because, well, I've fused 1 and 2 together, but, and then and 1 and 3 and 4 together, so in equation, schematically I did something like this. But I could, of course, also fuse 1 and 3 for suitable configurations. So for example, if x3 sits here, I could also fuse 3 and 1 together, because they form a sphere, and I can move that sphere by a conformal transformation back to the unit, or they lie inside some common sphere, and I can move this sphere, for example, by conformal transformation back to the unit sphere. So, so I again have a state operator correspondence, but now on this sphere. Sorry, an operator product expansion on this sphere. So I can fuse 1 and 3 together also, and 2 and 4 together. And then, so for suitable values of the x's, I can also write a different conformal block decomposition. like so. Delta I, yes, like so. So now I have two different conformal block decompositions for the same function. And there is a common non-zero region where both of these sums are perfectly fine and convergent. So this should equal 1. And this is the constraint. This is called the fact that these two sums should be equal to the same thing is called crossing symmetry. So we learned two things now. I want to highlight two lessons. One, if someone gives you all the 2-point functions, so all the deltas and all the 3-point functions, so all the lambdas, so the deltas and the lambdas, delta i's and the lambda ijk, then I can compute the 4-point functions. Because the 4-point function in the conformal block decomposition, I see that all I need to compute the 4-point function is just the lambdas and the deltas. And if you give me all of those, then I'm done. I just have the conformal block decomposition. It's convergent. And where it doesn't converge, I can just get it by analytic continuation. So the deltas and the lambdas, they determine the 2-point functions and the 3-point functions. They determine the 4-point functions, but also the 5 and the 6 and all the higher point functions, because I can just do the operator product expansion a bunch of times in a row to reduce it ultimately to something like this. So determine all n-point functions. For example, if you have a 5-point function, you do something like this. If you have a 6-point function, you do something like this. Right? You just fuse operators together, you fuse another operator, you fuse another operator, and so on and so on. So another miraculous simplification of conformal field theory. The 2-point functions were super simple. The 3-point functions were super simple. They were fixed all in terms of a few numbers, rather than being entire functions worth of information. All you need is a few numbers. And even more miraculously, that's all you need to compute all the correlation functions. The 4-point functions, they contained these arbitrary functions of the cross ratios. But if you look at the conformal block decomposition, they're completely fixed in terms of the deltas and the lambdas. So CFTs are really quite miraculous and very special theories. So that's the first lesson. The second is, let me look at the crossing equation. Let me ignore the whole fact that I'm trying to compute a 4-point function here, and let's just look at what I wrote here. Here's an equality involving lambdas and deltas, and between two functions of the positions, functions of the x's. And this equality involves the lambdas and the deltas with known functional dependence in the conformal blocks on the xi. So in some sense, I can view this, if you just give me an arbitrary set of deltas and lambdas, I mean, that set of lambdas and deltas that you gave me may not at all satisfy this condition. So the deltas and the lambdas have to be pretty special in order for this condition to be obeyed. In fact, in order for similar conditions to be obeyed for all the possible 4-point functions. So the second lesson is that crossing symmetry constrains the deltas and the lambdas. So this is also pretty neat because the deltas and the lambdas, they depend on the theory. So normally you would need to compute them, for example, from Feynman graphs or from maybe some lattice simulation gives you estimates for these scaling dimensions and these lambdas. But here we have an opportunity to try and see if we can determine these lambdas just from pure thought, just from these consistency conditions, which follow from very general CFT principles, and see if we can use these crossing symmetry. So now we can try to see if we can use these crossing symmetry equations to determine the deltas and the lambdas. So let me ignore the fact that this was a 4-point function, and let me highlight that this is just a highly non-trivial set of consistency conditions for the lambdas and the deltas. Notice that this is an entire function worth of consistency conditions. The deltas and the lambdas are just numbers, but this equation needs to be obeyed for all the x's. So it's really, really non-trivial. Okay, I want to highlight, do a little bit of a qualitative discussion in maybe the next 10 minutes, and then I may have to skip a lot of the unitarity conditions, but it's not terrible, I think. So, question that naturally comes to mind with this, once you have these crossing equations and you look at them, is can we solve them? Right? Would this give us an avenue towards computing the OPE coefficients or the 3-point function coefficients and the scaling dimensions in a general conformal field theory just from solving these equations? So that's the question. And what I wanted to say is, let's think of a few ideas. I'd just like to stare at this equation for a bit because I want to sort of convey its importance and also sort of the ways people have thought about these equations. So first of all, there are infinitely many equations. Like I said, even for a single 4-point function, I get infinitely many equations because I have infinitely many different positions to consider. But then there are also generally infinitely many operators, so there are infinitely many 4-point functions, and so definitely there are infinitely many equations to solve. What happens generally is because you have infinitely many operators is that also this sum is not a finite sum. And every single crossing equation in general, generally speaking, contains infinitely many terms. These are infinite sums. So you have infinite equations for infinite unknowns. Well, that's a little disappointing because it would be nice if this was just some finite equation and you would have a finite set of unknowns and you would just generally be able to solve it rather easily. That happens in special cases. For example, in 2 dimensions, you can use the power of the Virasoro algebra to write even bigger blocks which take into account the full Virasoro symmetry, and then you get often, well, in certain cases you get finitely many unknowns. You still have infinitely many equations, and then it's rather trivial or rather easy to solve for the unknown. So that's easy once you know how to compute the blocks. In very special cases like free theories, you get finitely many blocks and therefore finite sums, and it's also easy. But in general, you have infinitely many equations for infinitely many unknowns. So that complicates things a little bit. So how else could you attack these equations? Well, you could try, maybe is there some perturbative expansion? Perturbation theory in what? There's no coupling in principle, so this is just a bunch of lambdas and deltas. None of them need to be small. But one thing you can try, and this is in fact something that people have tried, is do an analysis where you take the x's very small or very close, the xi very close to each other. So you can take xi minus xj close to 0 in some limit, maybe a limit where they come close to 0 in Euclidean space. But you can also imagine continuing this and doing an analytic continuation in time to Lorentzian space and then taking a like limit. And this light cone limit, I'm not being very precise here, but there is a light cone limit that you can take where you can actually say something very nice about these crossing equations. You cannot solve them, but you can get some consistency conditions from them that are super nice that I won't have time to discuss that come from this light cone, from studying these crossing equations in the light cone limit. Another thing that people have tried to do is look at, for example, cases, special conformal field theories where there's a small coupling floating around. For example, the Wilson-Fisher fixed points. Where there's a small number, epsilon, in the game. And then you can start from a known solution, for example, the free theory, and you can try to solve the crossing equations order by order in the epsilon expansion. And this also is something that people have done in the past few years, and it's given some pretty neat results for data, conformal data, the deltas and the lambdas in the Wilson-Fisher fixed points. So these are two examples that I know that people, about people trying to solve this in some kind of perturbative manner. You can also ask, are there simplifications somehow in special theories? And the answer is basically that this only happens if you have enhanced symmetry. In 2 dimensions, it happens with Virasoro symmetry, where you have finitely many blocks. And in 4D, it happens in supersymmetric theories. In certain cases, some supersymmetric cases, you also have some simplifications of this system, where you can say something using techniques, that I won't have time to discuss. It's really a consequence of Virasoro symmetry or meromorphicity or so on. But there are rare cases where these things simplify, and then you can get much further and sometimes solve them completely. Ask me about it later if you want to know about what happens there. So that's another way you can attack them. You can ask, can we do something crude? Can we do maybe a truncation? So could we say, we know we have infinite sums here, but let's just say that we want to, or we know in most cases we have infinite sum, but let's just truncate them to a finite sum here, finite sum there, and see if we can get something. Obviously, with finitely many blocks, you can show relatively easily that with finitely many blocks, these functions are so that you will never, in general, be able to solve these equations. But you can try to find with an approximation, so with finitely many blocks, you can try to find an approximate solution to the crossing equations. So that's what I mean with a truncation. Now this, of course, is not quite controlled, because what's an approximate solution to this functional equation? Maybe you want to solve it for a bunch of x's, but not for all of them. Which values of x do you want to solve it for? Which values of x do you not want to solve it for? All of this gets a bit hairy, and often what you get is an uncontrolled approximation. So it's not that you get, people have tried this, but you don't quite get very rigorous results from this kind of game. So truncating this to a finite sum is often not a very useful thing to do, because your approximations are controlled. And then there's one more thing which you can try to do, is constraints. And this is the thing that's been the most fruitful in the past few years, which is you look at this question and you say, well, can we solve it? And maybe the answer is no, solution is hard. But what about getting constraints on the spectrum from these crossing equations? And that seems to work very well. What you could do, if you just want to get constraints on the spectrum, you don't want to solve the full set, what you can do is just take a subset. So for example, you evaluate these things at a certain value of the position, then you get one equation that you have to solve. This equation you cannot, and even if you solve it, you're not done. And solving it is hard because you have infinitely many unknowns. But what you can say is that these unknowns, infinite in number as they are, must obey certain conditions. So for example, you can ask, can I solve this equation? There's some spins here, and so the spins ranges from 0 to infinity. Could I have a theory where there are no spin 0 operators appearing in the OP? So all the spins here, in principle, run from 0 to infinity. Let me try to see if I can solve it with spin ranging from 1 to infinity and throw away the spin 0 blocks. Well, that's a question you can ask, and as it happens, you can just evaluate this thing at a few points and find very easily a contradiction with crossing symmetry. And the answer to that question is no, and so you get a result. It's a small result at this stage, but the result is that there have to be spin 0 operators appearing here. And then you ask, well, what if all the spin 0 operators have dimension 100 and higher? Well, again, you can find a constraint. You show, no, the spin 0 operators there must be one spin 0 operator with a dimension less than 100. And, well, then you can play a further game, right? What about dimension 10? What about dimension 5? And at some point, so you can analyze these constraints, for example, by evaluating at many different positions, or taking derivatives at a symmetric point or whatever. You get finitely many equations, and from these equations, you can get constraints on the spectrum of the form that I've just explained. So this is something we'll come back to, hopefully, tomorrow. So this works extremely well, and we'll look at it in more detail tomorrow. Another idea I should mention is, and this is not a way of solving it, but it's definitely an idea something that pops into your head if you look at these equations, which is how to compute the blocks. Because I told you in principle they're computable, but you have this nasty differential operator. It acts on a 2-point function. You have 2 of these differential operators, you just get a mess, right? And it's not an easy thing to compute. So this is a technical question, not a conceptual one. But it's a very important one nowadays because we want to derive these constraints, and to derive these constraints, in particular with numerical approaches, we need to accurately compute conformal blocks. So this could be a lecture series in itself, and I will have very little to say about it, especially because I'm running behind schedule. But it's a very important question. And some pioneering work here was done by Dolan and Osborne in the 2000s. And since then, we have many sort of results, and sort of we've made much progress in devising useful methods for computing conformal blocks. So this is a little industry where people try to compute conformal blocks for various representations of the conformal algebra. Here I've written down the equation for scalars, but what if I look at the 4-point function of tensors? I have new blocks, and there's a lot of computational room to do lots of intricate computations to do this, to compute these conformal blocks. So as an example, they are, in the end, known functions. So for example, in D equals 2, the conformal blocks have been known for a long time, and they are delta L for scalar operators. Let me say scalars, and let me take them all to be the same scalar because that's useful. So delta 4 equals delta 3 equals delta 2 equals delta 1. Then the blocks as a function of the delta 1 and the xi look like x12 to the 2 delta 1, x34 to the 2 delta 1. And then some function z to the h H, H, 2F1, H, H2, H, Z, Z bar to the H bar, F, H bar, to H bar, Z bar, like so. And then we add the Z bar swapped, like this, where I've now introduced some new variables, so I should mention that Z bar is U, 1 minus Z, 1 minus Z bar is V. U and V are the cross ratios that I wrote in the previous lecture, or one of the previous lectures. Like so. So this defines the Z and the Z bar, and the H is delta minus L, H bar over 2. H bar is delta plus L over 2. And the F is a hypergeometric 2F1 A, B, C, Z equals a sum, n equals 0 to infinity, A and B and C. And I don't expect you to copy this. Like so, and this AN is gamma A plus N over gamma A. So that was a long equation, but this just goes to show that these things are sometimes computable, and you can see this find this in closed form. So the Z bar. So if you give me the cross ratios U and V, I get the Z and Z bar. Those are the arguments of the hypergeometric functions here. And these hypergeometric functions are just defined in terms of some Taylor series in my coordinate Z with arguments, 3 arguments A, B, C. In this case, they happen to be H, H2, H. And the coefficients of the Taylor series are expressed in terms of these things. They're called Pochhammer symbols, but it's really just a ratio of gamma functions. So long story short, if you know how to compute gamma functions and you know how to sum Taylor series, then you can compute conformal blocks in 2 dimensions. Again, these are not the Virasoro blocks because I'm ignoring Virasoro symmetry. These are just blocks for the SO 1,3 conformal symmetry. In D equals 4, there's a similar expression. It looks very similar. D equals 6, there's a more complicated expression. And D equals 3, the odd dimensions are a bit more difficult. People have found convenient expressions for the conformal blocks as some implicit series. But they don't have this nice sort of hypergeometric form. So they look a bit nastier, but there are papers out there that just give you recipes for computing these conformal blocks in terms of some series expansion. So this is important, but not something I'd like to dedicate more words to. Okay, I'm basically out of time. Do people have questions at this point? Yes?
For example, but when we say, if someone is doing in the Lorentzian signature, but you would bother about the time ordering. So then, I mean, is it guaranteed that you can take, say, 1-3 operator and then 1-2, and that the results are supposed to be the same? So what my question is essentially that can you get these crossing symmetries in the Lorentzian signature as well?
Yes, crossing symmetry works in Lorentzian signature also. You can ask more generally for which complex values of the x's do both of these converge, right? Because you can just take the x's to be arbitrary and complex. And it basically converges as long as you can wrap 1 and 2 in a circle. So it's actually, and then of course you can if it converges in Euclidean signature, then what do I want to say? I mean, if a sum is absolutely convergent and you add some phases by going to complex values, right? You're guaranteed to have convergence in the full complex disks. So this tells you also where things converge for complex.
So do we get that by annually continuing back to the Lorentzian signature, or can one do it just in the Lorentzian signature ab initio?
Yeah, I think you can do it in Lorentzian signature, but I would not recommend it. I think it's much easier to just look at this in Euclidean signature first.
So in order to know the full set of primary operators, do you need to define a specific theory, or you can?
Yes. Yeah, to know the set of primary operators, well, an operator is, yeah, so the full set of scaling dimensions, that's just theory dependent. So sure, there. I mean, a theory at the level of correlation functions of local operators, everything is specified with just a bunch of deltas. It's an infinite list of deltas and an infinite set of lambdas. And that's it. So you have to just give me the deltas and the lambdas, and then they have to obey these kind of equations. And if all the equations are obeyed, then that's a consistent set of correlation functions.
So you just have the integer value of the scaling dimensions, and you have the operators without degeneracy?
The integer values of the scaling dimensions?
Yes, they have the integer values.
They don't need to have integer values.
Half integer?
They don't need to have half integer values. They can have arbitrary real values in principle. In a unitary theory, they're real, and well, we'll see shortly. In the next lecture, we'll see that they're bounded from below, but they can have real values. So no, they're not necessarily integer value. So this primary can have this delta can be an arbitrary positive real number up to conditions that we'll get to, and then these are integer shifts away from it. But this number is not necessarily integer.
Are there any way to check the result from Bootstrap, our constraint? Are there any method to check this result? Maybe from ADSFT or other kinds of method?
Experiment? No. I mean, the constraints will tell you that sometimes they will isolate the deltas to lie in a very narrow range. And that's just directly measurable. So yeah, you can check this against experiment if you want. But so experiment gives you a prediction for the deltas and the constraints. So the measurements from experiment better lie in the region that is allowed by your constraint, right? If experiment tells you that there's a CFT with no scalar operators appearing in an OPE, and you have derived that constraint, then your constraint is probably wrong. And well, of course, so and ADS CFT and supersymmetric theories and spheres and integrable models and the theories with Virasoro symmetry, all of the solved models give you consistency conditions that, like all of the known CFTs, you better not rule them out, right, with your consistency conditions. But that's all I think these things can do, including ADS CFT, in the context of matching against a constraint.
Another question is there any intrinsic difference between the Euclidean signature and Lorentzian signature when we use the conformal bootstrap?
Yeah, in Lorentzian signature, you can derive new results, for example, from the light cone limit, but there's also a thing called the Reggie limit and so on. So there's no fundamental difference. It's just analytic continuation of these equations to different points. And if you take the axis complex, you could be in Lorentzian signature. If you take them complex in the right fashion, then and then you're in Lorentzian signature. And if you can get some constraints from these equations, from this range of x's, then good for you. You have a new constraint on CFTs. So practically, you get very different constraints whether you're in Lorentzian or Euclidean signature, or at least that's what humans seem to be able to do at the moment. Conceptually, it's really these equations for complex x's, and so there are no new equations that I can write if I just consider correlation functions of local operators in Lorentzian signature.
So maybe in the different region, different operators dominate. Is it
Yes.
true?
Yeah, that's true. So in the Litecoin limit, what you see is that operators, the Litecoin limit that I did not write down, I just wrote some abstract thing, x is going to 0, but there's a specific Litecoin limit. For example, what you'll find is that in that Litecoin limit, the operators that dominate are the operators with very large spin.
Yes, thank you.
Okay, so further questions can be asked in private, and we are going to resume 11:10. Thank you.